Okay, you're here, hopefully, because you're JavaScript developers. You're comfortable building things for the web, perhaps writing things in Node, building Electron apps, but you haven't built hardware. You don't know how to take those skills to build real interesting gadgets. What I want to do today is show you some live coding, some live demos, and some bits of live electronics, and show you how you can take those existing skills, a couple of off-the-shelf components, and start building things in the real world. To do that, we need to dive into some details first. Unfortunately, I don't have a slide clicker with me, so the first thing we're going to do is build one. This is a MetaWare C. We'll take a closer look in a second. The important things are that it has Bluetooth and a button. We can connect this up with a watch battery, which is all it takes, and then we can immediately start writing JavaScript that runs on my laptop that uses this as a control. That looks something like this. We've got two Node libraries pre-installed, Node MetaWare, which comes for this board, and Robot.js, which is going to let us simulate key presses to do the actual slide clicking bit. This is a Bluetooth device, so the first thing we need to do is actually search for it, much as you're used to with any other typical bit of Bluetooth. And then when we find one, let's log, hey, we found this device. Great. I'm actually just going to wrap this in a little function here. And this is all just fairly standard JavaScript that shouldn't be too unfamiliar if you've been writing other JS. So at this point, if we've got here, we've managed to do a Bluetooth scan, and we've found this device. So now we want to connect to it. So that's nice and easy as well. We do this, and that gives me kind of classic Node.js error callback kind of thing. And from here, I then need to check, did we get an error? If so, let's log it. And then let's just try again. Great. So if we get here, that's all the code we need to get a JavaScript process on my laptop talking to this little bit of hardware in my hand. So from this, let's actually start listening to it. We've got a button on here, so what we want to do is connect to that. So we say let button equals new device dot switch. It's a slightly weird API here, but it works. And then we have to register for button events. And this is something you'll find with a lot of boards like this. But for power and bandwidth reasons, they're not constantly transmitting from all of their sensors, even from buttons. So you need to go through and individually enable each thing that you want to hear about. So we say, I'd like to hear about button events. And then we say, when the button changes, I'm going to do something with that. So, particularly if the button's just been pressed down, then tell me about it. But also, then trigger a key press. And just pretend I've pressed the right key. So hop forwards through my slides. I'm also just going to add an extra bit of logging here so I can tell when this actually is working. And just in case for when this goes wrong, let's say if it gets disconnected, then I'll want to just log that too. Disconnect. And try again. This is all fairly simple JavaScript. This is 35 lines of code. And we can immediately start building interesting tools. So let's try and run this. So that now is going to do a scan searching for Bluetooth devices. If we give it a couple of seconds, it should find this device and print found device. Any second now. Can you feel the tension? Maybe. Okay, let's try one I've done earlier. So, again, we're just doing the Bluetooth scan here. Perhaps this is already connected to my phone, which would be annoying. Oh, it's connected. Excellent. OK, I'm going to go and work out what broke there in a minute. So we've connected to this now. We've got everything hooked up, and we should be able to hop straight across to these slides and immediately start clicking through. There we go. Yes. OK, this is pretty cool. It's slightly more awkward, but you can still get it working in front of an audience in a couple of minutes. Do you remember that first time that you built anything for the web? That first web page you put together, big shiny red text, that's a beautiful moment in itself. There's this magic there when you suddenly realize the internet isn't something you can visit, but something you can understand, something you can change, and something that you can create. And you can get that same magic with hardware. You can buy some small off-the-shelf components, you can write a little bit of JavaScript, and you can immediately build useful tools. So, what is this? This is a small microcontroller board. It's got Bluetooth, a battery, a button. It's also got a bunch of other sensors on it, so we can detect accelerometer and get movement, gyroscope. We've got a temperature sensor, an LED, and then GPIO, general purpose input-output, which we'll talk a bit more about later. What this lets you do is immediately start writing code that reaches out from your machine. This comes with firmware already on it that exposes all of these sensors with a nice convenient API so that you can immediately start accessing that and immediately write JavaScript that reaches out of your machine. You don't have to think about how this works. You can just connect and start making interesting things happen around you, building useful gadgets. So, what kind of useful gadgets? This is what I always find is one of the harder parts for getting into hardware. What are your ideas? Where can you go with this? One of the easy ones is to just add sensing to things around you. You've got a motion sensor here. Attach this to your chair. Every time you sit up, every time you stand up, lock your computer automatically. Easy, simple bits of JavaScript that you can run to script things around you. And you can start adding sensing to anything else you like and running commands based on that on your machine. And similarly, you can push information out from this. You can do notifications. So every time your tests fail, for example, you can sit this on your desk with a little glowing green light when everything's good, turn it red when everything's bad, and set it up so that if you tap it, it reruns the tests. Simple, interesting little gadgets that you can put together in tens of lines of JavaScript using standard libraries. Unfortunately, though, we're still a bit limited here. This gives you a cool, neat gadget that you can use, but doesn't let you really see the details of what's going on. And if we want to try and get into more low-level interactions, you want to use some different kind of components. And a really popular option here that I'd recommend is the Arduino. So I've got one of these down here. The Arduino has 32 kilobytes of storage, 2 kilobytes of RAM, a 16 megahertz processor, 60 megahertz 8-bit processor. This is an extremely minimal computer, but that means that you don't have any distractions when you're building on this. This board is not running an operating system. When you put code on it, your code is all that's running on it. And you can directly control everything that's going on and see exactly how the hardware works. There's a few interesting parts to pay attention to here. We've got a USB connector up in the top left, which is where I'm getting power and communication through to this here. We've got a microcontroller in the bottom right, which is where all the magic happens. And then we've got pins across the top and the bottom. And this is how you get connectivity into these. So these pins have labels. I'm not sure if you're going to be able to see those. Oh, OK. Each of these pins do different things. And this is something you'll find for lots of other kinds of boards as well. So on the left, first, we've got power pins. So these are providing fixed, constant power. We've got a 3.3 volt pin, a 5 volt pin, 2 ground pins, and a couple of other ones for various special cases. And these let you build sort of traditional fixed circuits. You've got some pins that can do analog reading a little further around here. And these let you automatically understand interactions coming in from around you. So if you want to read temperature information, for example, these kind of analog changing values, you can read that in. And what you're actually doing here, particularly, is reading voltages set on these pins. You've got pins on the other side to do digital read and write. So these let you read a high voltage and a low voltage, but nothing in between. So you can tell whether this pin is set or not. And for these pins, you can set them to high or set them to low, but you can't graduate between those. And then a few of these actually also support analog write. So this uses something called PWM, pulse width modulation, where they very quickly change from high to low to simulate a value between. And this lets you control things like motors, where you want to dynamically change the speed of the motor. All of this puts together gives us a platform on which we can start actually building hardware. So, the other thing you're going to need to connect components to this is a breadboard. If you're not familiar with breadboards, these might be kind of scary. It's not really clear what's going on. They're actually very simple. Under the hood, these are connected together. These pins across the top have 2 rails that by convention are used for power and ground. And then each set of 5 pins across the board is connected together to allow you to connect components easily. This lets you put together a bunch of wires on your desk without it immediately becoming a horrible mess. It will eventually become a horrible mess, but this gives you a bit more control to add slightly more structure to things and more sensibly set up your system. So a simple circuit is going to look something like this. Who's done some basic electronics that looked like this before? Yeah, maybe a third of the room, something like this. Okay, so this sort of basic stuff should be pretty easy if you've done any of that before. I've got the Arduino down here that you might be able to see. All we're going to do is connect up the ground pin, as we had in that diagram, through to that ground rail. We're going to connect up the 5-volt power through to the power rail. We're going to connect a resistor from the power through to one of these across here. And then we're going to connect an LED through there. And just like that, we've got working power coming through. We can do basic electronics immediately straight off this board. So that's pretty interesting. That's not really powerful, though. There's no JavaScript here. You're here to write JavaScript. So how can we dynamically control electronics from this? The actual electronic changes you need to do that are very simple. We want to move from the fixed 5-volt pin to pin 8, which is one of the digital write pins, where we can write whichever voltage we'd like. So that's nice and easy. I unplug from over here, and I plug in down here. And now my LED is off. There's no voltage coming out of this pin right now. What I need to do now is write some JavaScript that controls what's going on here. I mentioned before this has 2 kilobytes of RAM. As you might have noticed, if you use Chrome, you cannot run a JavaScript engine in 2 kilobytes of RAM. You're not going to be able to put JavaScript directly on this board. There are some other boards where you can do that, but generally with much less of a community and an ecosystem around them. However, you can still write JavaScript that directly controls this. There's a firmware that comes with the Arduino, which exposes the entire API that you would have on the board over the USB connection. So I can write effectively the equivalent code that I would write in C and compile for this board and run it in JavaScript on my machine, and then that will send commands directly through. And the actual library to do that is called Johnny 5. Johnny 5 is an extremely popular option for loads of boards for this kind of thing. It supports the Arduino, but also, I think, around 30 others, a very long list. And anything where you're thinking about this kind of coding, where you're directly writing to individual pins, Johnny 5 is a really useful tool to be able to do that. Let's have a go at that. So we've got this circuit, that's set up here. Let's write some code to control it. So over here, I've got Johnny 5, included Temporal, which we'll talk about in a second, and a board. And what I first need to do is connect over the USB and say, when I'm actually connected, I'd like to run some code. And I'm going to get the pin and say new 5.pin 8. Cool, so that's that pin 8 digital write pin that I want to be controlling. And I can just set the voltage high, just like that. And that will immediately turn on the LED if I run this. That's not particularly interesting, so let's blink it by hand. What that looks like is this. Every second, I like to turn the pin on, and then half a second later, I'd like to turn it off again. And this is going to blink our pin back and forth. I'm using Temporal here instead of the built-in timing libraries. Generally, that's what you want to do if you're doing any timing with Johnny 5. There's quite a lot of cases where some specific hardware can be quite sensitive to timings, and Temporal lets Johnny 5 directly take control of the timing loop and manage this itself. There's some details in there, but you don't really need to worry about them. Temporal gives you a very convenient way of doing timing that will just work when talking to hardware like this. So if we run this code, fingers crossed, it's going to blink an LED. So let's go over here, node index.js. We start that up. We connect down across through the USB here. That's now hooked up, and it's not working. Well, that's extremely annoying. Let's all look at how it's not working. Why is that not working? Okay, let's try one I've done earlier, where we directly write that like this. Have I connected the right pin? That would do it. Yeah, there we go. Cool. So we've now got a extremely quickly blinking LED here, and we can write a little bit of JavaScript. Let me show you the actual correct JavaScript that does that, which looks like this. We'll investigate that later. Okay, so we can get blinking LEDs working here, and we can immediately start writing to interesting components. We can also read from components with just a little more complicated JavaScript and circuitry. So that looks like this. Photoresistors, like this, let you read light, let you detect the brightness around you. So what this does is change its resistance according to how much light is visible on this resistor. What you might think that means you can do is put the power straight through the resistor and into one of the analog read pins. That will not work. What your pin does here is read changes in voltage, not changes in resistance. So you need to do a slightly more complicated circuit to make that work, which looks like this. This is called a voltage divider. You'll find this as a very common pattern for any sort of variable resistor. So resistors that change based on light, but also based on temperature. Things like dials, where you're turning a kind of analog dial to change resistance. All of these require you to set up a basic circuit like this. And what's happening here is that the power goes out along that rail through the photoresistor and then splits. And there's a circuit going through a fixed resistor, constant resistor, back into the ground, and a circuit going through into A0, our analog read pin. So let's set that up. Firstly, let me kill this. Okay, let's try another demo. So we've got a fixed LED here. Let's turn that off for a second. What we want is our convenient little light resistor, photoresistor here, into there. A constant resistor that goes into the ground. And then we want to read into pin A0 from that same row. What's going to happen here is that the voltage we receive on pin A0 is going to be proportional to the ratio of the different resistances here. So as the resistance on that light resistor changes, the voltage that we're going to be able to read coming into A0 is going to change. And what that means is that we can write some code that reads that pin, hopefully. So, can anybody see what the problem is here? I cannot, which is annoying. All right, rather than having this explode, I'm going to explain this one that I did earlier. So, here again, we wait for the board to become ready. We set up the connection, and then we read from pin A0. So this is our analog read pin, which is set up here. We then read every half a second the current value of the pin, and we just print that. And immediately, we should be able to read what's going on around us. So this is going to connect through and should start streaming through numbers in just a second. There we go. So it's currently getting an 18. If I cover this, that might be slightly less light, and it goes down to 14. If I don't know, point my watch at it, that might go up a little bit, 30. So the actual range here you've got goes from 0 to 1023. Here, obviously, we're only actually going from about 15 to 30. You want to be calibrating this effectively for whatever kind of situation you're in. And this, again, applies to photoresistors, but also thermistors, anything else where you're trying to measure an analog range. And to calibrate this, you change the fixed resistor. It's about the ratio between the two. So if you change out that resistor, you'll change the range of values that you see here. But we can immediately start writing code that says, if somebody points a light at this, run some JavaScript on my machine. Make some actual actions happen. When I turn on the light in this room, do something with my JavaScript. There's a lot to electronics. I'm not going to try and explain all of it, but Arduinos are a pretty good board with which you can get started here. There's a huge ecosystem and community around them that makes it really easy to pick up components and just start building. The Arduino starter kit is particularly good for this and comes with a lot of the kind of basic components you're going to want. Node ARDX is a website with a lot of tutorials specifically focused on Node. A lot of the other Arduino bits are largely focused on C, and though it's a direct translation, more or less, to read the code, it is easier with Node examples. Hackster is a website filled with people's hardware projects. If you're looking for inspiration, if you want to just work out how to build this weird circuit, somebody else has probably come up with something similar that you can look up, build yourself, and then play around with. So there's a lot of good suggestions in there. And generally, I just really recommend picking something up, getting started, and trying to build something useful for yourself. So what should that be? What kind of ideas can we come up with? The classic beginner project is a plant waterer. It's a clearly useful thing. If you have plants in your house, you should be able to automatically water them. And that's a circuit that is only slightly more complicated than what we've looked at here. You get a resistor that, you get a sensor that can read the moisture from your soil. You plug that in, and you read it just like we've done here. And when the moisture in your soil drops below a certain point, you turn on a pump that adds some water. And you can add whatever extra logic you want there, timing, internet controllability, anything you like. But that gives you immediately useful things you can start putting in your house to automate stuff in your life, to build interesting gadgets. One project I found on the internet that I really quite like, it looks at automating inbox 0. So this is a circuit that's slightly more complicated than ones we've looked at so far, but only a little bit. It looks like this. That's a switch there on the right. What happens with this circuit and the JavaScript, which is in that GitHub repo up there, is that if you hold down this button, a yellow light turns on, and a couple of seconds later, another yellow light turns on, and then a few seconds later, that third red light starts blinking, and then it deletes all your unread emails, saving you time and effort. These kind of simple projects you can immediately just start building and putting together and connecting up to other things. Anything you can write JavaScript to talk to, any APIs, any other services, you can now connect through to the physical world. Okay, so Arduinos are cool for this sort of thing. They let you get more involved with the hardware and start to understand what's actually going on under the hood. They are still, though, quite limited. 2 kilobytes of memory is hard to stay within. You don't have a lot of power here. If you want to start looking at more complex things like video, you're really going to struggle on an Arduino. And while things like networking are possible here, they're much more complicated than they would be on other platforms. The typical popular platform where you get a lot more power is a Raspberry Pi. Almost certainly, almost everybody in this room, I suspect, has heard of the Raspberry Pi. It's incredibly popular and incredibly powerful for the price points. So these cost around $30, I think. This is the Raspberry Pi 3. This has a gigabyte of RAM, 1.2 gigabyte, 64-bit processor. You can run an actual operating system on. It's much more like a computer that you're used to. It's got Ethernet, Wi-Fi, Bluetooth, 4 USBs, HDMI, a camera port, all sorts of other exciting toys. And you can immediately start building much more complicated and powerful applications on this in an environment that you're much more used to. This can run Node directly on this machine, or any other language that you're really aiming to look at. So you've got a huge amount more power to get involved with here. This also has GPIO pins, which allow us to connect extra components. So much as we saw the pins on the Arduino that allow us to do certain things that each have different uses, there's sets of pins down here that we can start to connect extra hardware. One other simple bit of hardware you can put into here is cameras. So I've got 2 Pis here, in fact hooked up right now with Pi cams. And if I switch across, how do I get at the Wi-Fi on this resolution? Who knows how Macs work? Let's just try and do that, see what happens. Yeah, there we go. So, I've got 2 Pis here connected to Wi-Fi coming out of my phone because the conference Wi-Fi is touch and go, as I suspect we may have all noticed. What these are currently doing is acting as simple internet-connected webcams. So each of these right now is streaming video through to the internet. You should be able to, if the Wi-Fi works. Even my Wi-Fi is not going to work, although it thinks it works. Let's just, yeah, there we go. What you should be able to do is go through and immediately connect to these and see video coming live out of them. So I've actually got their local IPs connected just to make that a bit more reliable, and we should be able to see here some nice video coming across. That's a lot of you over there. Let's point that down. The light makes it a bit tricky, but you look lovely. Let's go across down here, and we've got another webcam over on the other side for all of you lot. So these are two simple JavaScript applications running, connected up to the internet, streaming video directly. This is pretty interesting and pretty powerful. I'd like to do something a bit more complicated with this. So what I've actually got here are two hats. So there's you could directly connect hardware to the GPIO pins here, but for the Raspberry Pi, there's a large community of hats, pre-built bits of hardware, already wired up together. So this is the Enviro hat, which comes with light and color sensors, a barometer and temperature motion sensors, plus some extra analog pins, and also comes with a 40-pin connector that directly clicks onto a Raspberry Pi. This means you don't have to do the low-level breadboard and wiring. You can just buy off-the-shelf hats and directly click them into the Pi and just get moving. So what I've actually got attached to these two Pis here right now is a blinked hat. This is probably the cheapest, simplest toy you could get started with here. These are 8 RGB controllable LEDs, so we can set the color for each of these individually and the brightness for each of these individually, and they are quite bright. So I've got both of these connected up over here. Let me show you. Tiny little components that you can very easily click straight on and off, and which we can write JavaScript to control. So let's have a go at that. Third time lucky. Right, so over here, this is the current code for the server. The entire thing is 40 lines. We're going to stay fairly simple here. How's that for size? I'm going to make that a bit smaller just so you can see what's going on. Let's go down to 16. How does that look? Readable from the back? Yeah. Okay, so we've got a little bit of error handling here, and then we're just using Express and a video streaming library called RaspiVid Stream. Express you may well be familiar with if you've written any Node servers. We've also got Express WS, which lets us attach WebSockets to Express so that we can stream data directly, here, video. This server has 2 endpoints. If you go directly to the server, it serves up index.html, a very simple website. So index.html, there we go. What this does is pull in a library that does video decoding. It then creates a canvas, sets that up, and connects the canvas to the video stream WebSocket endpoint. So this expects to pull video frames from the server and put them in a web page. And that's what you saw there with that video that we're displaying. We're using a library called Broadway under the hood here, which does video decoding in JavaScript in the browser. Very easy to get set up with like this. The actual video stream endpoint is only slightly more complicated. When you connect to it, we log, we tell you how big the video is, the dimensions. We get hold of the video and flip it, because the cameras are upside down. And then every time a frame of video comes through, we pass it through onto the WebSocket and we send it up to the browser, and then we log any errors. So when data appears from the video, send it to the client. And when you leave, we stop sending you video. And then the remaining logic just starts up the server and logs errors. This entire thing, 40 lines, lets you build an internet-connected webcam straight out of the box. The hardware for this costs about $50 in total. If you want to buy a nice internet-connected webcam off the shelf, you're looking at $100 plus. And you can build this in 40 lines of pretty simple, readable JavaScript. Let's try and change it and actually use this blinked we've got here. So first, we need to import blinked. Require node blinked. Then we actually get hold of the LEDs, so that's a new blinked, and we register them, set them up. So we're now connected to this little hat that's on top of here. What we want to do is set all pixels and just turn them all on, maximum brightness. and then you call send update to write that, to actually put that into action. That's going to be quite bright, so let's turn it off afterwards. That is going to look something like this. A second later, I'd like to go clear all, and then send update again. So this means when we run this code, as it starts up the server, it's going to flash brightly, and then continue. Okay. How do we actually run this code? How do we take that JavaScript I've got and put it on here? It's actually a fairly complicated problem. This is a Linux machine. As you might be aware of, how to deploy code to Linux machines is an exciting and open topic that there are a lot of people coming up with interesting answers to. This is much like how do you put code on a web server, but with a bunch of extra complexity. This, for example, is not running the same processor architecture that your machine is. You cannot just copy node modules across and expect it to run. Any native modules need to be recompiled for the correct architecture. And you've also got a bunch of interesting security problems and so on. To actually set this up, you're going to need to go in and flash SD cards yourself. You're going to need to configure an operating system from scratch. How many people in this room would be comfortable securely configuring a Linux machine from scratch? Few hands here and there. Yeah. Not the rest of you. It's not particularly easy to do. It's certainly not something you want to do really quickly, and it's not something you want to repeat. Raspberry Pis do break, SD cards corrupt over time, and you really don't want to have to keep reconfiguring this from scratch, especially if you do it slightly differently each time. You're going to have to install your dependencies. So there's a module I have to apt-get to get hold of the video drivers, for example, cross-compiling things, your native modules, actually putting your code from your machine onto here each time round, making sure that that works the same way every time and that you can tell whether it works, and then actually keeping all of that secure. You want to set up an internet webcam in your house, but you don't want everybody on the internet to be able to connect to that. And you certainly don't want everybody on the internet to be able to do whatever they like inside your network. So there's a bunch of interesting problems here. There are quite a few different solutions, as you might imagine, for the same kind of problem we have with DevOps for web applications. But the one that we've really found successful at Resin is Dokka. Dokka is pretty good in data centers and servers if you've tried that out. In fact, how many people have tried Dokka? How many people have used Dokka? Oh, yeah, good 50%. Okay, yeah. So Dokka is pretty great in servers and data centers, but really comes into its own in IoT. For these kind of solutions, Dokka is fantastic. If you're not familiar with Dokka, but you are familiar with virtual machines, you can think of it as very much the same thing, but much more lightweight and quick. Dokka lets us build an image of what's going to be running on our device, an image of our application, the frozen state of all the files that are going to be involved within our application, and what's going to be run when it starts up. And it then lets us move this image around between machines, start up a container from it, run that for a while, kill the container and start it again, and start from exactly the same place and get that reproducibility. So that reproducibility is really important and comes from isolation. Dokka lets you build an image and define your application separately from the rest of the OS. So you can have a very simple configuration for your operating system that defines basic networking, and you can then define your whole application declaratively in a Docker file, in a bit of text, that you can clearly say, okay, I have this apt module configured with these settings, I have these files installed, and you can then rebuild and change and know exactly what's going on. Also, we gain distributability here. You can build your Docker container on one Raspberry Pi, move it to another Raspberry Pi or a new one, and immediately have it work and do the same thing. So Docker is a really, really powerful tool for a lot of this. You still need to actually set up an operating system to run Docker. Fortunately, we have one of those. Resin OS is an open source operating system. This is completely free and open source that we make, which is a stripped down version of Docker that runs designed for IoT devices, so it improves reliability. In the cases of network and power failure, it drastically reduces the amount of traffic on the wire when you're receiving updates. And critically, it runs in a very low memory environment compared to where you might be normally used to running Docker. And Resin OS also comes with everything you need for standard network configuration and so on. You can download it off the internet, write it to an SD card, and then just treat this like Docker and ignore all the other details completely. What that means is that once you write that to an SD card, turn it on, you then can just ship code by running resin local push. So this is a single command line which immediately starts connected to this. Under the hood, this is really just a wrapper for Docker. We take your code, we give it to Docker on the machine, which builds it and starts it up. So if you're using Docker, this may be very familiar, but this immediately lets you get started doing some interesting things. So we've got our code over here. Let's do that. So what I'm going to do is push this to this IP, which I should check first. Yeah, that looks promising. Let's try and see. What this is going to do is connect to that Docker container over there, stop the existing camera application we've got, automatically manage restarting it and bringing it back up in a second. Once we get into the Docker build here, you'll notice that we get a huge amount of caching. So we've got to wait for this node server to shut down. Slowly but surely. There we go. And we get a huge amount of caching. So we've gone straight through caching for all of the node install, all of apt-get and installing my video binaries, and all of the npm install, because I haven't changed any of that. It's now just copying across the files which I've changed, those extra things. It's starting up that new container, and it's streaming back the logs, which should start up a new server in just a second, and flash the lights. And just like that, we can ship code. And you can get that feedback cycle, even for IoT, down to the order of 10 or 20 seconds. For a lot of IoT, for a long time, it's been a lot worse than that. But Docker allows you to do this kind of thing really easily and much more directly connect your workflow to what's running on the device. So this is pretty good. What you'll find quite quickly is that you actually end up with devices all over the place. You end up with remote devices. You have something at work when you're at home, or at home when you're at work, that you want to be able to push an update to, or to reboot, or to control. We also make Resin IO. No? Okay, no, I think we're good. We also make Resin IO itself. This is our commercial platform, but it is free for anybody with 10 or fewer devices. So unless you're planning on going out and buying 500 Raspberry Pis tomorrow, you can immediately just get started attaching your devices to this. And if you are buying 500 Raspberry Pis tomorrow, do come and talk to me first. What this actually gives you is a remote dashboard into your devices, so that you can remotely connect to them and see, wait for it, that you've got your device here, it's running this, you can read all your logs directly from the internet and directly control them. You can also SSH in straight from the web and all this kind of thing. More interestingly, we can deploy to devices that aren't directly next to us. Deploying to a Docker machine on your local network is great, but has limitations. You don't want to expose Docker to everybody on the internet. So we want to be able to also deploy this to everybody else in the world. So to do that, I'm just going to commit blink. And then I'm going to push that to Resin. And that's going to do a cloud build once in our cloud builder. So we actually have ARM servers in the cloud to compile things across for ARM. And then it's going to download magically over the internet across onto here. So even if you do have 500 Pis, you can build once and ship to all of them. Or if you're sat at the office, you can git push changes and immediately see them in action in your home. You can immediately get those kind of changes coming through. And again, we get a lot of these same kind of caching benefits. We'll just leave that going in the background. So, yes, so you can git push code straight away. So, what can you do with this? What interesting gadgets can you build with Raspberry Pi? There's quite a few options here. I think a digital photo frame is actually a really good one if you're looking for something to get started with. If you're used to the web world, a photo frame is effectively just a web application. It shows pictures, maybe you can swipe between them. It pulls pictures from an API that it shows somewhere. That's a quite simple app you can put together, and I've got a link in the bottom to one I've put together that just pulls photos from Facebook and uses React to give you a nice swipeable UI you can flick through. You can get hats for the Raspberry Pi that you can click directly on top that give you a screen and the touch support as well immediately without having to do any complicated electronics. And you can instantly start building a useful gadget in your house that you can then iterate on, focused on the web side, so that you don't have to get immediately too much into the hardware. And you can then start attaching other things. So I've got a motion sensor, for so on and so on. You can start building more and more complexity on top of an interesting, useful base. Another quite popular, interesting option, again, is building plant waterers. So Arduinos give you a good base to do basic things with this. With a Raspberry Pi, you can now set up a camera pointing at your plant. While you're on holiday, you can check how it's doing. You can remotely water it. You can check the internet, see what the weather's doing, and water it more or less. You get a lot of extra power using cleverer boards like this, where you can run all the JavaScript you know and love directly on the board, directly next to your plant. Okay, so we've got a couple of minutes left. Let's wrap up. We've talked about 3 major areas here. Firstly, remote sensors. There's a lot of boards you can get, like the MetaWare C. I've also got the Nordic Thingy. Both of these are about $30, $50, that kind of area, and let you immediately use Bluetooth to just reach out from your computer and build software that does something in the real world. You can start to get into microcontroller boards that give you much more direct access to the hardware itself and allow you to click together components and really start to understand and play around with electronics at a low level. And single board computers like the Raspberry Pi. There's also things like the BeagleBone. Intel had a whole range of Edisons that were quite popular for a while. All of these allow you to run much more complex applications. Allow you to treat them like a real computer and do anything you might want to do with a real computer, but at the cost of a bit of extra complexity. And we've looked a bit at how Dokka can help you manage some of those problems. That's everything I've got for you today. I am PimTerry on Twitter, and I will stick these slides out later so you can go through, and there's URLs all the way through with each of these examples if you want to check them out, have a play with them yourself, and they've all got lists of exactly the kind of hardware you're going to need to get started with. If there's one thing I could leave you with, it's that hardware is really not that hard. With off-the-shelf components that are very cheap and easily available, you can use your existing JavaScript skills, some easy libraries straight off NPM, and immediately start building interesting, useful gadgets and making hardware that gives you that same feeling of magic in your hands once again. Thank you very much.